Hello, AP Stat students. Today we will be doing 9.3a significance test for population means. When working with population proportions, we used a z-test. Since they are based from the z-values from a standard normal distribution. When working with population means, however, we use t-values. So t-statistics, t-tests, and t-distributions from a t-distribution with n-1 degrees of freedom. To keep it straight, we have what is known as a ZAP tax. And so what that means is z-test for a proportion, t-test for a mean, and we use x to represent mean. So z-test for proportions, and so you can keep it straight too. T for a mean. The conditions are pretty similar. You've done them over and over. So the conditions for population means using a t-distribution. We talked about this last time. The data comes from a random sample. So you can infer to the population or a random assignment, randomized experiment, sorry. So you can establish cause and effect. This condition is very important. For the normal condition, we introduce the fact that you must graph if either of these arise. So you must graph to check to see if the normal condition is met. So sample size less than 15, use T procedures if the data appear close to normal. If it is skewed or has outliers, do not use T procedures. For sample size at least 15 but less than 30, the T procedures can be used except if the data has outliers or moderate to strong skewness. And finally, if the samples are large enough, then T procedures can be used even for clearly skewed distributions. And so the sample size has to be greater than or equal to 30. And last condition, independent. Individual observations are independent. So if we sample without replacement, the 10% condition must be met. So the population is more than 10 times the sample size. All right, for our calculations portions, when doing a significance test, we need to calculate the test statistic, and from there we can figure out the p-value. So we perform calculations assuming that the null hypothesis is true. So going back to our null and alternative hypotheses, the test statistic measures how far n differs from the parameter value, and in this case our parameter value is the null value, the mean, specified by the null hypothesis in standardized units. Due to our t-distribution, our test statistic is, so when we were doing proportions, we had our standardized z-score. Here we will have our t-score, and our t is equal to our sample mean minus the null value divided by the sample size over the square, or I'm sorry, the sample standard deviation over the square root of the sample size. And so this will give us our t statistic, and then we can calculate our p-value. So when the normal condition is met, this statistic has a t distribution. Remember, t distributions were had a larger spread and were flatter with n-1 degrees. Okay. Still single peaked, still bell-shaped, but just not as normal looking, so to speak. Once we have calculated the test statistic, we can use table B or a calculator to find the p-value, the probability value for a significance test about the mean. So using a calculator to compute p-values from a t-distribution, you still go to your best friend second vars. So go to second vars instead of choosing normal CDF, which we always did for z-scores for proportions, we use a t-CDF. So make sure you use a t-CDF, and then we'll fill in the prompts. So you have a lower bound, you have upper bound, and then you have a degrees of freedom. So there we go. Right, let's do, let's look at the four-step process. So the four-step process in your state portion, always want to test, always tell what you're doing. So test the hypothesis that the true mean of whatever at and then make sure you put the significance level, whether it's 0.05, 0.10, whatever. List your null and alternative, and then tell what the parameter means. In the plan portion, for the significance test for means, you are going to use a one sample t-test for means, and then check the conditions, the random, normal, again, graph here. On your test, though, since you're not going to be able to graph, just tell me what your graph looks like, and that will suffice if I give you a problem like this. And then the independence condition. In the do portion, if you're given a list and you're not given the sample mean or sample standard deviation, remember, do a one variable statistics. But if it's given to you, then you don't have to worry about it. Compute the test statistic, and there's your formula. Find the p-value. So here I wrote it again. If the alternative hypothesis is going to be greater than, then your lower bound is your test statistic, your upper bound is 100. So if for some reason you got your null hypothesis is whatever, the mean is greater than 25, then you know you are going to use this scenario. If the alternative hypothesis is less than, then your lower bound will be negative 100. Your upper bound will be whatever your test statistic is that you get. And if it's not equal to, then you're doing a two-sided test. So just take whatever your multiply by 2, or just type in 2 first and then go to second vars and hit tcdf. Right. And then the conclusion, interpret the results of your test in the context of the problem. And let's fix this. Since our p-value is not less than, so since we're always going to compare if it's less than or not less than. If it's not less than our significance level, then we fail to reject the null hypothesis, and we don't have enough sufficient evidence, yada, yada, yada. And if the p-value is less than, we reject the null. And then just tell what your conclusion is in there. Give the alternate conclusion. Let's do an example. Every road has one, at some point, construction zones that have much lower speed limits. To see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed in miles per hour of a random sample of 10 drivers in a 25 miles per hour construction zone. Here are the results. So obviously it's a small sample. We are going to have to graph and check. Darn. Problem. Can we conclude that the average speed of drivers in this construction zone is greater than the posted 25 mile per hour speed limit? So it kind of tells you how to write your hypotheses. So in the state portion, we will test the hypothesis that the true mean speed of drivers is 25 miles per hour in this construction zone, where the null hypothesis is 25, the no difference, and the alternative is the mean is greater than 25. So notice the notation, you're no longer using p, you're using mu. On a test, don't try and take time trying to find the symbol for mean, just write mu and that will suffice. And then also we need to put, because I didn't, at the 0.05 significance level. wasn't given to us, but we want to use that. Where mu is the mean speed of drivers in the construction zone. All right, in our plan portion, if conditions are met, we will perform a one sample t-test for means. Let's look at our conditions. Random sample of 10 drivers. And remember, you don't just check it off and say it's random. There we go. Tell why it's random. For the normal condition, we know that 10, our sample size, is not greater than or equal to 30. So I took the time to enter the data in, and then I knew I had to graph it. So this is what the graph looks like, and we'll save time. You all know how to graph. So you all know you have to enter the data into a list and go to second y equals to get to the stat plot, and then you want to graph your data. So this is what mine look like for this particular problem. Something like this. Try my best here. So you might get a little worried over here with this point. And if you're worried, you want to do a modified box plot. And I did one of those also. And I saw skewness, a slight, but I did not see any outliers, even though that looked like it was. So always check another graph. You can even check a histogram if you want to, and that'll help you determine if the normal condition is met. So this is close enough to being linear. So linear, no outliers. So it's robust. Right. And for the independent condition, it's reasonable to assume that there are more than 100 drivers in that zone. All right, and now in our do portion, again, I took the data, did a one variable statistics, and I got my sample mean to be 28.8. My sample standard deviation was 3.938. And now we can calculate our t-statistics. So our t is our sample mean minus the null, which is 25, divided by the sample standard deviation over the square root of the sample size. That gives me 3.8, or I'm sorry, 3.8 divided by 1.2453. And I got a t-value of 3.0515. So visually, so here's like a really bad, probably t-distribution. That's okay. So visually, here's 3 out here. So this is a very small chance of, it's a very small probability here. And so we are going to do a TCDF. So a TCDF, and this is 0, just for a reference. Our lower bound is going to be our test statistic because it's greater than. Okay. So our lower bound is our test statistic. So 3.0515. Upper bound can be like 100. And our degrees of freedom is 10 minus 1. And that will give me a p-value 0.00687. Now compare that to alpha, our significance level, and that is definitely less than 0.05. Since our p-value is less than 0.05, we reject the null hypothesis. There is convincing evidence to conclude that the average speed of drivers in that construction zone is greater than 25 miles per hour. All right. Part B, given your conclusion in Part A, which kind of mistake, a type 1 or a type 2 error, could you have made? Explain what this mistake means in this context. So if we remember what type 1 and type 2 errors were, a type 1 error means to reject the null hypothesis when it's true. A type 2 error means you fail to reject the null when it's false. Well, since we concluded that the speed of drivers is 25 miles per hour, we rejected the null. So we could have rejected the null when it was true. So that would be a type 1 error. We determined in our conclusion that the average speed was greater than 25 miles per hour when it is not. So going back to memories of type 1 and type 2 errors. Okay, now example number 2, this another sample. A college professor suspects that students at his school are getting less than 8 hours of sleep a night on average. To test his belief, the professor asks a random sample of 28 students, how much sleep did you get last night? Here are the data in hours. So 28 students, darn, we have to graph. It's okay. Lucky for you, I put in this data and graphed it beforehand. Do these data provide convincing evidence in support of the professor's suspicion? Carry out a significance test at the 0.05 level to help answer this question. So in our state portion, test the hypothesis that the true mean hours of sleep college students get is 8 hours. So our null is 8, and he suspects that it's less than 8. So where mu is the true mean hours of sleep a college student gets. Okay. Plan. We will perform a one sample t-test for means. Simple random sample of 28 students at the college. Check. The normal probability plot shows, so we know 28 is not greater than or equal to 30. So this is what our graph looks like. This is the normal probability plot that I will sketch for you. And I'm not going to put like all 28 dots or whatever. Maybe I will. No, I won't. Okay, but it looks like that. Again, if you're apprehensive and you don't think it's linear enough, do a modified box plot, which is what I did for this one also. And it is linear with no outliers. So again, it's robust. You don't have to write that, but do explain here. Okay. And then for the independent condition, it's reasonable to assume that there are 280 students here at the school. So all right, again, I did a one variable stat. Sample mean is 6.643 hours. Sample standard deviation is 1.981. Our t statistic is 6.643 minus the null, 8, divided by 1.981 over the square root of 28. Numerator gives me negative 1.357, denominator 0.3744. Our t statistic is negative 3.625. So visually, again, a bad drawing, but right here, again, very small probability happening. Okay, so okay. So to do a TCDF, our lower bound this time will be some number to the left of that, so negative 100. Our upper bound will be our test statistic, which is negative 3.625, and our degrees of freedom is 27. That gives us a p-value. This is what you'll see on your calculator, 5.9139 e to the negative fourth. So remember, that is just the same thing as moving the decimal point over 4 places to the left. So 1, 3 zeros, and then the 59139. That is definitely smaller than alpha. Oh, wow, I did not put that. That just reminds me, in the state portion, at 0.05 significance. We should always put that in our state portion, what level you're testing at. And so since our p-value is less than alpha, we reject the null hypothesis. There is convincing evidence to conclude that college students get less than 8 hours of sleep on average. This is an average. There we go. So make sure you put that on average in. All right. Let's do a two-sided significance test. We don't really do those often. In the children's game, Don't Break the Ice, small plastic ice cubes are squeezed into a square frame. Each child takes turn tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are too difficult to tap out. The machine that produces the plastic ice cubes is designed to make cubes that are 29.5 millimeters wide, but the actual width varies a little. To make sure the machine is working well, a supervisor inspects a random sample of 50 cubes. Hallelujah, we don't have to graph. Sample size is large enough. Every hour and measures their width. The output summarizes the data from a sample taken during 1 hour. So if you look at the data in the table, it gives us the sample size in the first column. It gives us the sample mean. It gives us, I'm going to skip the standard error for a second. It gives us the standard deviation, and then it gives us the 5-number summary. Here, the standard error of the mean is just the standard error. And so what that is it takes the standard deviation, so it takes the sample standard deviation, dividing it by the square root of the sample size. So it gives us the denominator for our t statistics. So that's great. And we don't have to calculate it. It's already given to us, so that makes it a lot easier. Do these data give convincing evidence that the mean width of cubes produced this hour is not, so here's the key word, not 29.5. Doesn't say greater than, doesn't say less than, it says not. So in our state port, so two-sided tests. In the state portion, test the hypothesis that the true mean width of ice cubes is 29.5 millimeters. The mean is 29.5. The alternative, the mean is not 29.5, where mu is the true mean width of ice cubes. Plan, we will perform a one-sample t-test for means. Random, it's a simple random sample of 50 ice cubes. Normal, 50 is greater than or equal to 30. So it's normal, no matter what the distribution looks like. So you don't, not that you can graph it anyway, and you don't have individual values. Okay. Independent, there are reasonable to assume there are more than 500 ice cubes produced. Okay, so in our do portion, we don't need to write down our X bar or or sample standard deviation or any of that. We can just go straight to our t-statistic. So our t-statistic is equal to our sample mean minus our null, which is 29.5, divided by, now if it helps you to put in everything in here and you don't want to just jump into using this right here, that's totally fine. It's totally up to you. I'm going to put it in there. And you could have just done 0.0935 divided by the square root of 50 gives you the same thing. But if it just helps you, you do it that way. So the numerator is negative 0.0126. Denominator is 0.0132. That gives me a t-statistic of negative 0.9545. Now notice this is a two-sided test. So you're going to have to do a 2 TCDF. So type in 2 in your screen on your calculator before you even go to second vars. And that takes care of that. Or just do TCDF and multiply by 2. Okay, our lower bound is negative 0.9545. Our upper bound, oh, I'm sorry, I said that wrong here. All right, so our lower bound is negative 100. Our upper bound is our statistic. Okay, and our degrees of freedom is 49. Okay, that gives me a p-value 0.1722, which comparing it to alpha is not less than 0.05. So since the p-value is not less than 0.05, we fail to reject the null hypothesis. There is not convincing evidence to conclude that the cubes do not measure (29.5 millimeters) on average. Okay, and then something was bothering me up here. Again, I left off this part. Hopefully you caught it though. All right, we will wrap up 9.3a by talking about the connection between two-sided significance tests and confidence intervals. Unfortunately, the significance test doesn't tell us the actual value of the parameter. For that, we need a confidence interval. The connection between significance tests and confidence intervals is even stronger for means than it was for proportions. That is because both the test statistic and the confidence interval use the standard error of the sample mean in the calculations. So when the two-sided significance test at a level alpha rejects the null hypothesis, the 1 minus alpha % confidence interval for mean will not contain the hypothesized value, which is the null parameter. And when the test fails to reject, and I'll explain what all of this is in the last example here. And when the test fails to reject, like it did in our problem, the ice cube problem, the confidence interval will contain the true parameter. We'll see that. So this we're going to see in the last example here. So looking at, going back to don't break the ice, if you look on the left side, it has like the sample size, the mean. This one calculates, this is some software, it calculated the confidence interval for us. So here's the confidence level, 95%. And how is it related? Well, if you looked at the problem above, that was 1 minus that gives you the significance level, which was alpha 0.05. And here is the confidence interval. So from 29.469 to 29.514 millimeters. So we first need to interpret that confidence interval. So going back to the last unit, let's interpret that. So in A, we are 95% confident that the interval from 29.4609 to 29.514 captures the true mean width of those ice cubes. In part A, would you make the same conclusion with the confidence interval as you did with the significance test in the previous example? Well, in our previous example, we failed to reject the null. So the answer is yes. And here's why. Because 29.5 falls in the interval. And so because the null value falls in the interval, that's why we failed to reject it. Okay, and in part B, again, it's a really good review interpreting the confidence level. So I can do it right here. If we took many, many samples the ice cubes, approximately 95% of the intervals. So if we took many samples and calculated the interval for each of those samples, approximately 95% of the intervals would capture the true mean width of the ice cubes. So a good review on interpreting the confidence interval and confidence level and seeing the connection between significance tests and confidence intervals. So those are your notes for today. Have a great day, AP Stat students.